Ja, goedemiddag. U luistert naar het webinar Submicron en microdeeltjes karakteriseren in polydisperse en heterogene suspensies met hoge resolutie. En deze presentatie vindt plaats door Dr. Tiziano Sanvito. Hij is de uitvinder van de spestechniek, waar hij straks meer over zal vertellen, en directeur van EOS, de merknaam achter de Classizer One. Aan het eind van het webinar bent u in de gelegenheid om vragen te stellen. En ik geef nu graag, dat kunt u trouwens in de chat of even naar mij doorsturen. Of gewoon even in bij questions uw vragen beschrijven. En achteraf zullen we die dan behandelen. Voor nu geef ik graag het woord aan Tiziano. Tiziano, you can start the presentation. Thank you. I'm sorry, but yeah.
Thank you very much. Well, it's a pleasure to be here and to have this opportunity to present to you all Classizer One as a novel particle analyzer for the characterization of heterogeneous system. It's not a traditional device. It's something that provides insight on heterogeneous media and mix of different kinds of particles. A brief presentation about myself. I'm the sole administrator of EOS. I'm a physicist by study, and during my PhD, I developed the basis of the method with some of my colleagues. And we founded a few years ago EOS with the mission of develop devices of a new solution for the analysis of particles in fluids. But let's go and let's start. EOS has been founded in 2014 with the mission of providing new solution to particle size analysis market. The method is patented. There are different patents covering different aspects, and it is unique from different point of view. We have presently different publication. We have different collaboration ongoing, and the device has been marketed since 2019. We are represented in Europe by several companies, and thanks to Inventec for this opportunity for this webinar. And Inventec is our local representative in the Belgium, Netherlands, and Luxembourg area. But let's start with the technical aspect of the seminar. Particles. Why to size particles? Why to measure particles? Because they are present in many fields, starting from pharma up to pigments, cosmetics, foods, and so on. And today we will focus our seminar, our webinar, to pigments and to the process control of pigment production and formulation. So, how to measure them? How to improve formulation based on them? There are different tools on the market. There are different methods to achieve this task, starting from the static light scattering up to single particle scattering, dynamic light scattering, nano-tracking analysis, as well as non-scattering methods, let's say culture counter and direct visualization, microscope, scanning electron microscope, and transmission electron microscope. These methods are wonderful. In this case, all the particles are perfect, more or less uniform spheres, all with the same shape, of the same material. The real problem comes when you have to measure real formulation in real target liquids where there are many different kinds of particles, different kinds of, let's say, pigments. Maybe they are aggregates, some of them are mesoporous. Maybe you have to analyze structured particles with a non-uniform aspect, for example, core shell particles. And maybe you have to discriminate the particles of your interest, also in presence of other populations, let's say scraps, contaminants, and so on. This is a mess if you try to measure this system with traditional method, because traditional method provide an average information about the whole system without the possibility to classify and separate the contribution coming from the different populations of particles in suspension. We focused on this topic, and we discovered and developed a new approach called single particle extinction and scattering. How it works briefly. We have a vial with the sample. We flow the sample the liquid with the particles through a device using a peristaltic pump or a syringe pump in the most easy way. And we enlight the particles using a special focused beam. When the beam illuminates the particles, we study the interference coming from the transmitted light and the scattering light in the forward. So we have the superimposition of the transmitted beam as well as the scattered one. And on the sensor, a system of fringes appear when a single particle transits through the beam. From the analysis of this system of fringes, we can retrieve different information, different independent information on the single particles illuminated at that time. From the dark fringe, we are able to derive the extinction, let's say the extinction cross-section of that particle. From the visibility of the fringes, let's say the bright one minus the dark one, we are able to derive the polarizability of that particle. Plant, we count them because it is a single particle device. So we know how many particles per milliliter exploit different optical properties. And it is natural to measure different particles and create a two-dimensional histogram, which we call EOS clouds. In this histogram, we plot the extinction cross-section versus the polarizability. And the clouds are the sum of single events. So we measure different particles, we sum them, and we obtain clouds depending on the optical properties of the particle. So in case of an heterogeneous system as this one, more clouds appear, and the user can measure and classify heterogeneous system looking to the clouds, can measure the relative concentration of different population, so different excipient, API, or different kind of particles in suspension, and monitor how the clouds behave and change in real time via continuous flow approach, as well as for a batch-to-batch analysis via principal component analysis. But this is the classification, which is the first part. But you can also interpret the data. Basing on optical theorem and scattering models, we are able to interpret particles in terms of the size, comparing the experimental data directly to theoretical data without any calibration. And for each single population, the device defines the best optical properties, let's say the best refractive index, and provide to the user the particle size distribution corresponding to the selected population. So in a heterogeneous system, you are able to classify, quantify, and size all the particle population presence, regardless of the complexity. Advanced insights are provided. For example, we are able, starting from the optical parameters, to derive other information, as for example, the aggregation state, the thickness of a core shell, or the aspect ratio of a non-spherical system. Few examples. This is a very academic case. We have a system of polystyrene monodispersed. As you can see, a single cloud appears in the graph. The position of the graph, of the clouds in the graph, is compared with different theoretical lines, and the best one is selected. In this case, the system defined the refractive index of 1.58, compatible with the material, which is polystyrene, and automatically count the particles defining the numerical concentration, as well as the principal parameters of the particle size distribution, or the whole particle size distribution is provided, or the oversized analysis of the distribution can be retrieved. Some technical information. The SPES works starting from 200 nanometers up to 20 microns, considering the electric spheres. If we consider absorbing particles, we can measure starting from 100 nanometers. Typical working concentration are from 10 to the 5 up to 10 to the 7 particles per milliliter. While the latter one is demanding to avoid the so-called pile-up, so the presence of more than one particles per time in the media, the lower one is just suggested. So you can rely on the method also to measure particles in almost pure liquids. It's just a matter of statistics and time. The measuring time in this regards is typically about 10 minutes, 15 minutes for most of the samples. For monodispersed system, even a couple of minutes can be enough. For a really polydispersed system with an heterogeneous number of particles in terms of optical properties and concentration, more time is required to gain the required statistics to be able to define with the needed affidability the presence of secondary populations. But it's just a matter of time. A very important thing that I have to stress is that the system works on a single particle level. So if we measure for a longer time, the statistics increase as well, because we do not rely on the convolution or inversion algorithm. We count particles, we size them, and we define the particle size distribution, summing up the signal. So more time means more statistics, just when needed. The system works with a flow, as briefly introduced before, typically ranging from 0.1 up to few ccm. But this number can be customized on request, and higher flow can be managed, changing the fluidics. From the chemical point of view, the wetted surfaces are quartz, Teflon, and PEEK, and these guarantee a very high chemical compatibility with most of the solvent, and it is easy to clean, relying also to strong liquids, to surfactants, as well as to acid, just when needed, of course. The size accuracy is very high. We have different validation with monodispersed system of different material, as well as the repeatability is very high, and accuracy in terms of the numerical concentration. We published on our website different application notes where many data and many technical information and example of application are presented. Feel free to study them and come back to us for any question. But let's start with a very nice example. This is the force and the power of the method. In this system, we have a mix of two different particles of different material, but the same size, polystyrene and PMMA. As you can see, two different clouds are detected, and the two different clouds lie on different theoretical lines. So the system enables the user to discriminate the presence of two different kinds of particles. We are able to select the first or the second population, count how many particles there are in an absolute way or in a relative way, and to understand that the two different optical properties has to be considered for a proper evaluation and measurement of the system. The same with polydispersed systems in terms of size as well as in terms of optical properties. In this case, an emulsion of silicone oil is mixed with a suspension of polystyrene particles. As you can see, two clouds appear on the map. The first cloud is compatible with the expected position represented by the red line for the silicone oil emulsion, but the user can focus the analysis on the secondary population and retrieve all the statistical parameters also in this heterogeneous system. So you can classify particles and select particles of your interest and focus the interpretation and the analysis of the particles on just a single portion of the total volume or the total population in the sample. Just a brief introduction of the layout. It is very easy to use, very user-friendly. We have a sample. We have just to flow it through our device and start the acquisition with the software. Different peaks of a possible application are both this one. We can rely on high quality peristaltic pumps. We can rely on syringe pumps. You can rely also on sample manager and auto sampler. We are developing our system, but you can also couple our device, our sensor to your auto sampler, to your sample manager. The system is able to communicate, and custom data protocols and communication protocols can be developed to be able to communicate with your already existing system in your lab. As in this case, we couple our system with a commercial device made by an FFF, a spectrophotometer, and a dynamical scattering. In this case, we couple our system with a more complex fluidics. So we are able to provide also custom solution ready to be used in very particular and tailored applications. So you can couple our system with spectrophotometer, inflow particle detector, a synthesis reactor for pilot analysis and pilot reactor systems, process real-time controls, and so on. And you can perform the analysis batches to batches or inline online in real time with 1 second time resolution. Our unique analysis can be applied to different heterogeneous systems. Let's say, starting from the point of view of the product on the market, tablets, powder, capsule, creams, let's say liquid solution, all aspects of different pigments, of different inks, watercolors with the Godot, for example, powders of pigments, microcapsule, we have colors inside, creams as oil painting. Maybe you want to study the environmental behavior of the particles or how they behave in the aerosol if needed. But the most important part is that we are able to manage complex situation again. System where you have a principal component, principal population of particles, and a secondary population, which can be an excipient, which can be another kind of particles, or can be an impurity. So maybe you want to control the quality of your pigments while you are formulating it without any filtration or purification. So different cases can be considered. An homogeneous system of particles mixed together, so a heterogeneous system of homogeneous particles, and an homogeneous system of heterogeneous particles, or more complex situation as core shell system, mesoporous system, or non-spherical particles. And the analysis can be also extended to behavior analysis, quality control, also in target fluids. So particle stability, aggregation, wetting, absorption of liquids, as well as interaction with surrounding media. So we manage complexity, opening the possibility to measure particles in such complex systems. Let's start with some examples about inks. Let's start with commercial inks. These are examples of application with commercial inks from the bench. Out of the shelf, you can take a few droplets of the ink, disperse them in the proper solvent, and measure them as they are. For the sake of the eye, the red line is the same for all the particles, and it is the expected position for titania, 2.4 in terms of refractive index at our wavelength. As you can see, the white, which is made by titanium, is in agreement with the expected theory for this material, but the other particles not so well, because absorption play a role. So we are able to identify the presence of absorption. We are able to classify particles in terms of their optical properties, let's say how they interact with the light. So we are able to provide a more complete information and image about the system you are formulating or you are studying. Then you can leave the device, decide the best optical properties, or you can input your own numbers in terms of absorption as well as the scattering, and retrieve the numerical particle size distribution, the cumulative particle size distribution, as well as the oversized analysis. Especially in these cases where the particles are smaller, the study of the oversized analysis is essential to study how many particles larger than given thresholds there are per milliliter. This to improve the formulation. This to reduce the probability to have larger particles that can be stuck in the printer head. This to improve the quality of the pigments in terms of the color and the brightness. All this information can be provided online. All this information can be provided offline, and PCR analysis can be also used for a very advanced batch-to-batch analysis and quality control. A trick. Let's check a standard case where we can work. you have a mix of different inks. You have to study how many particles of a given type there are and how many particles there are per milliliter, and if the system is stable in time. We can provide this kind of information. This is a mix of a black and a white ink. As you can see, if we measure the natural provided raw data is a system of two clouds, the user can select the first one and select the second one to retrieve the numerical concentration of the first population as well as the numerical concentration of the second. So in a mix of different inks, we can work using the optical properties to define the presence of different kind of particles and quantify them and check if they are stable, because if they are stable, since the system works on single particle level, in the final map we have to obtain more or less the sum of the single components. If there is an interaction or an instability, different clouds appear, or different shapes of the clouds can be detected and investigated. Moving to more complex system, let's focus on the analysis of watercolors as a reference. In this case, I provide you some example of application with watercolors. As you can see, a more complex system is detected, and different kind of population can be observed in different colors. As you can see again, the red line is the expected position for titanium in agreement with the white color, which is a Chinese white, so it is something made by titanium particles. But as you can see, different optical properties are detected for other colors: black colors, red colors, green one, yellow, and blue. And especially as you can see, the blue one and the green one is made by a mix of different particles, different excipients, different pigments. So we are able to follow the formulation and the stability of the formulation in this situation. Again, the numerical particle size distribution can be retrieved for all the samples, the same for the cumulative particle size distribution, as well as for the oversized analysis. The user can input up to 10 threshold of his interest, and the system provides to the user the relative concentration of each threshold or the absolute number of particles per milliliter detected for each threshold. Depending on the application, the user can decide which is the best representation of the numbers. But again, where is the added value? The added value can be also related to the milling or to the quality control of a process inline or offline if needed. With pigments, we typically milling or grinding is needed to reduce the size of the particles up to given value. And the study and the characterization of the oversizes is essential to guarantee a given number of particles lower than a target number or a target value. In this case, we present the real case of a black pigment. We start with the bulk, and we know that for an okay, let's say, from this process, we have to obtain a number of particles larger than 200 nanometers, lower than the 40% of the total population detected. We start with the mill, and we measure the system. As you can see, the numerical particle size distribution, again, cumulative particle size distribution, and as well the oversize can be retrieved, and can be retrieved also for a single component in a heterogeneous system. So if you have also components, let's say population related to other particles or to lubricant or to other component of the formulation, you can measure and focus the analysis on the pigments regardless to the presence of other populations. Again, I want to stress this. You can focus the analysis on single population in a heterogeneous system. Then you can mill again and mill again. As a representative example, let me show you these three cases. As you can see, after time, which means after milling, you change the particle size distribution as well as the cumulative size distribution, but also oversize. So you can apply the method to identify if the size, if the numbers, if the concentration of a given product is in agreement, is suitable for the process, and then go to the next step, looking for the optimum in terms of the time of the process and the quality of the product. But this means that you can also monitor let's say, monitor special situation where the stability play a role. For example, you have to wet powder, you have to synthesize a pigment, maybe you have to check the presence of aggregates or cluster in suspension, just to check which is the best mechanical dispersion system or the best surfactant for that product or for that formulation. We can monitor also these kind of effects because the aggregates change the optical properties of the particles. What does it mean? When we analyze an aggregate, we measure the effective optical properties of the whole particle. And the effective optical properties of the whole particle is an average between the monomers and the liquid between the monomers in a simple way. So the effective refractive index of an aggregate is lower respect the effective refractive index of the bulk material of the monomer themselves. And monitoring the particle size distribution as well as the optical properties detected by the method, we are able to identify the presence of aggregates and provide insight about the compactness of them to the user. And the compactness can be used to improve the formulation, simply changing different surfactant, changing different mechanical process for the milling or for the suspension and dispersion of the particles, and trying to reach the higher refractive indexes and close to the one expected. As you can see in this case, we have a dry suspension of titanium dispersed in milk water. As you can imagine, this is not stable. We can sonic it, we can steer it, we can disperse it. But in the end, this kind of particle size distribution is observed. The effective refractive index is lower respect to the tabulated one in the literature. This means that the system in suspension is not made by compact particles, but by aggregates. And relying on some algorithm, we can also estimate the compactness, and in this case, range from 20% up to 22%. Means that if we consider the volume of the aggregate, just 20–22% is made by bulk materials. But if we sonicate, we can change the size of the particles because we break the aggregates, as well as we can increase the optical properties. Means that the particles are more like single object suspended in the media. The same can be retrieved from the other point of view. We have a black carbon suspension in water, and we have to check if it change in time. The answer is yes, due to the clustering. And we are able to monitor the number of particles per milliliter changing per time, the refractive index of the final particles respect to the initial one, the compactness of the final one respect to the initial one, as well as the size of the aggregates. All this information can be provided in this condition, but also in heterogeneous systems. But can be provided also in line online with typically 1 second time resolution. In this case, I'm showing you the typical information retrieved during the control quality of a system during an inline online process. As you can see, we monitored the presence of particles in a stream for more than 7,000 seconds, but the system can work for all the hours you like, all the days you like. This is the average EOS clouds detected during the whole process, but we can see that there are different events. There is a giant peak here and small peaks here. We can select a single time slot, export the particle size distribution and the optical properties of the particle detected at that time slot, and compare the particles with our theory. and interpret the particle present in this peak. As you can see in this peak, a single polydispersed but narrow clouds is measured, and this means that we are measuring a lubricant, and this information is compatible with other information coming from the synthesis. So we are able to identify the presence of a leakage or an impurity in the process. And if we focus the analysis at other time slots, we are able to measure the presence of other kind of particles, the electric particles as well as absorptive particles, monitor them, quantify them, and follow them in terms of number of particles per milliliter in the media. So we manage complexity in terms of optical properties and in terms of time if needed. But since we measure a multi-parametric information, we can rely also on different statistical approaches as the principal component analysis and benefit from this kind of approaches for a quality control, very advanced quality control, batch to batch. What means that we can record different batches. These are the particle size distribution in terms of our properties of a polymeric system. And we have samples with some impurities, as you can see, very few in terms of a concentration. So we have more or less the same system. In some cases, we have a not perfect purified secondary population. How we can check the quality? How can we monitor that? If we rely on the particle size distribution, the contribution coming from this impurity is more or less negligible because the system measures just the primary component, the primary population. The same in terms of the whole concentration, you can neglect them, but maybe they reduce the quality of the process, the quality of the product. So you can apply principal component analysis. Means that you use some math, some algorithms which are already integrated in the system. The system define in the two-dimensional plot the presence of secondary populations and the presence of primary, it's a main population. As you can see, the PD, the primary population, is this one, which corresponds to the primary particle population. But the system defines also the presence of secondary population in terms of the optical properties. And automatically, you can plot the information detected thanks to the principal component analysis, and the samples are represented in terms of let's say, relative concentration of the primary population and relative presence of the secondary ones. So we can create quality regions comparing particles and samples coming from different batches, and easily we can define a classification of particles, not just in terms of the size, not just in terms of the concentration, but also in terms of secondary population, longer tails in particle size distribution, or presence of aggregates, difference in terms of the relative concentration between different kinds of particles, and many other things. So we can manage the complexity from a mathematical point of view, and it is very easy with a very user-friendly interface. You can compare the quality of batches of reference with new one, checking if the new one are compatible with the good one previously obtained on your historic data set. We published different papers and different application notes. You can find most of them on the website. You can check them. You can ask to us or to invent them. It will be our pleasure to present them and discuss them with you and understand together with you if our system could be a solution to your problem and fits your needs. Thank you very much for your time. It was a pleasure to present you the system, and please feel free to propose me any information, any suggestion, any question. It will be my pleasure to answer it. Thank you.
Okay, thank you, Tiziano. I have one question already for you. Someone is asking what particle properties, liquid properties are needed to have a good measurement, and She talks about refractive index, density, or something else?
Yeah. No, the system detects, let's say, the system works on a two-step level. The first step is the acquisition of optical properties, let's say the extinction cross-section as well as the polarizability, and the creation of the two-dimensional clouds. This is enough for a classification of particles and for a quality control in most of the cases. Then you can interpret them. For the interpretation, some constraints are necessary. For example, you can rely on misscattering. In the case of misscattering, if you assume that you have the electric particles, the system defines by its own the best refractive index for the particles and provide you the information, and provide you an information about their optical property, let's say the refractive index. It is something that is measured by the system. Of course, in case of absorbing system, you have to make some constraint again. Maybe you have to suppose the real part of their scattering, so you can define the imaginary part of the absorption, or you can set the absorption and define the real part. Or you can work with our dataset and data library to define the best optical properties, which can be used to describe a system with absorptive particles. You can, for example, compare the experimental particles, the experimental data, to different theories and define which is the best one or the most suitable for a correct interpretation of the data. You don't have to input from the beginning all the information. And about the density, we are not sensible to density from a physical point of view. We are sensible to optical properties, and sometimes optical properties can be linked to density. Of course, if we have two compact particles with the same, let's say, structure but different density, we are not sensible to them because we are sensible to the refractive index, let's say the electric constant of the material. But in a formulation, if we have a particle well dispersed or an aggregate with the same size but made by a cluster of smaller monomers, we are sensible to this. This is something related to density, but to optical density.
Okay, thank you, Tiziano. Another question. Do you have experience with hydrogel particles? There's hardly optical difference between particle and dispersion medium.
Yes, we have experience with these kind of systems. This, of course, the answer is depending on the case. We are able to provide information on this kind of systems. Why I'm stressing about case by case? Because hydrogel are typically not stable if you dilute more the system. We have to dilute the system to measure the particles. So the stability has to be checked and has to be monitored. And another aspect is the mismatch in terms of the optical properties respect to the media. Hydrogel typically have a refractive index very close to the liquid because of their nature. And this means that the amount of light scattered by a single hydrogel is lower compared to a bulk particle with the same size. So we have to change the sensitivity in terms of the size. For example, with hydrogel, we made some tests in the last years in other cases with some customers, and the size sensitivity was 300 nanometers in diameter or 400 nanometers in diameter. So we have to change the technical reference parameter. But in the end, yes, we are able to say we are sensible to them if they are in the range.
Okay, thank you. Well, someone else is saying interesting technique. Is it possible to get the presentation? I think we can get the presentations. Yeah?
All the information provided and presented to you are non-sensible, so feel free to receive them. I'm pretty sure that Wendy can distribute the presentation after the webinar, and of course feel free to ask us any technical information about the data, and if your device, your system can be measured with our method, we are at your disposal.
Okay, well, thank you. Well, we will be sending everyone and the presentation and the recording of the webinar, so you can
Thank you very much.
just watch it back whenever you like. Well, no further questions. Thank you very much, Tiziano. Thank you everyone for
Thank you very much. Thank you all. Feel free to come back to us for any question. If we can provide
any
the
questions
solution.
can be mailed to me,
Nice.
to Wendy van Leusden, and you can, if you don't have my email address anymore, you can watch it or
Thank you very much.
find it on inventor.nl. Thank you.
So